Okay, we'll look at, what is this? Stats models. So this is, stats models is a kind of Python module. Stats models, Python. And so we've looked at sklearn, and we'll probably revisit sklearn to see some more of its modules. But here's stats models, and this is useful for fitting kind of your classical statistics models, things like linear regression. So everything in like 102A, 101A, 101B will be covered in stats models and other things. So things like, so if you go to statsmodels.org, you kind of see the models that it'll let you fit, like linear regression and generalized linear models, which is for like logistic regression and I don't know, linear mixed effects, ANOVA, things like that, okay? And so I just wrote up a brief example in kind of notebook 8.2 where we could take, you know, the N-Haynes data with the babies and just fit a simple linear regression model, okay? So the kind of the two primary imports are import statsmodels.api as SM and statsmodels formula API as SMF, okay? So the stats models API uses kind of Numpy array notation, and stats models.formula API uses formula notation, which is similar to R's formula notation. Not exactly the same, but similar. Okay, so if you're used to making linear models in R with the formula notation, this should seem reasonable. Okay, so anyway, maybe I'll okay, there goes my kernel. So I'll import my data. We'll create our merged data set by using pandas merge. And then I'll filter this down to just babies where the age is less than 12 months. And we're just going to pull the columns age, gender, and weight. Okay. And then I use babies.columns is equal to age, gender, and weight. And this lets me just rename the columns. So, you know, if I ask for baby's head, it looks like this. So now I have gender, weight. So this just makes referencing them easier, right? And then if I call for information, you know, we have 399 entries. Okay. Oh, some people had been asking about if their data set is too small. And the answer is almost always going to be no, all right? So, you know, we're accustomed to living in this land of big data, and we feel like we need to have thousands of observations. But statistics actually started, I don't want to say started, but a lot of the drive for statistics was that data was scarce and expensive, and we want to make sure we can get all the information we could get out. So you would have data sets with maybe 30 observations, but it would be enough to do an analysis. And that was a lot of the kind of the driving force behind creating models like ANOVA and things like that. And the whole course, so your whole 101B design of experiments course, the whole point of that is to design your experiment in such a way that you can collect the least amount of data and make the conclusion that you're hoping to make, okay? And but you know, now we're in this land of tons of data, and we don't get to appreciate it. Okay, so for formula notation uses stats models dot formula dot API, okay? Often imported as SMF, okay? So the stats models dot formula dot API. So you'll use SMF.OLS, okay? And then here we're just going to say weight by age and gender, okay? And the way gender is coded is currently coded as a numeric variable, 1 for boys and 2 for girls, which is technically not correct. So gender is currently coded, 1 is boys and 2 is girls. And the way in the current OLS call will treat gender as a numeric variable. Okay, and that's technically not correct, but it doesn't matter, all right, in this case. And why would it not matter? So even if I change this and I coded it as a categorical thing, why doesn't it matter that gender is treated as numeric here? Because we're going to get the exact same results. Do you know why? Yeah, because there's only 2 categories, okay? And so the difference between boys and girls coded as 1 or 2 doesn't matter if it's coded as 0 or 1 either, okay? It's as soon as we throw in a third variable though, then it makes a difference, okay? So if we have something like red, yellow, and green, okay, and these are our 3 categories, then and red is 1 and yellow is 2 and green is 3, then having somehow those numbers imply those numbers would imply that green has 3 more of something and than red. Okay, so that red has, sorry. So yeah, because there's only 2 categories, it's not going to make a difference whether it's 0 or 1, 1 or 2, or 0 or 100. I mean, it might change the scaling on that, but if you have multiple values, you know, the difference between red and yellow, and the difference between yellow and green, and the difference between red and green, those might not be, I don't know what the right word is, commutative. So, you know, if they're coded numerically, the difference between red and yellow is 1 point, and the difference between red and green is 2 points, and maybe that's not correct, okay? But if you only have 2 categories, it doesn't really matter, because you get the same difference. And so anyway, you define your model. You say stats models formula OLS, and then you do model.fit. Okay, so this just instantiates the model, doesn't actually do anything. Then you fit the model, and those will be our results. And we could ask, here, let me just, if I do print results, it just tells me we have this, okay? I could do print the results summary, which is similar to asking for a summary of a linear model in R, and it presents all of this information. Okay, so we get OLS regression results, and it has, says all of this information. It presents us, the R-squared values and the log likelihood and the AIC and the BIC and all of this stuff. It gives us our coefficients, okay? And so we can see, age being in months, we can see each month the babies gain about 4.36 pounds. I'm sorry, 0.436 kilograms, so 436 grams. And the difference between boys and girls looks to be that, girl is coded as 2 and boy is coded as 1. So adding 1 to the gender variable would seems to decrease on average about 732 grams overall. Okay, and we could see that the p-values associated with all of these things are pretty much 0. Okay, if you do have a value that is a category, okay, so you can use this function, capital C, and you throw in the categorical variable in there, and that's going to take. So all of these things are kind of coded up in such a way to kind of the categories are expected to be listed numerically, but then you kind of specify to the model that we have a categorical variable, so we have C gender here. Okay. And then so we run that, we do the same thing, so I've called this model 2, and then we would fit the model 2.fit, and then we would print out these results, and we see that the numbers, oh my, now I'm in trouble because it's not exactly the same. Why is it not exactly the same? My intercept has changed. The coefficient for gender and the coefficient for age is exactly the same. I don't know why the gender intercept has changed. Okay, I got 399, 396. Let me just see. Okay, this is weird. I don't know what the difference is. Okay, well, the gender coefficient is exactly the same, and the age coefficient is exactly the same, right? 4363, negative 0.7327, yeah, 0.4363 and negative 0.7327. I'm not sure why the intercept value changed on me, though.
My intercept stayed the same.
Your intercept stayed the same.
Yeah, I'm not sure.
Did I do something wrong? Let me just run through this.
Not sure.
No, I'm sure you did. You're doing just fine.
I'm just trying to copy you. So.
Yeah. Okay. Okay, I got model, weight defined by age and gender, fit the model as results. Okay. Model 2, weight defined by age and gender and category, fit the model, print the results.
Actually, wait, no, you're right. I used the same results.
Oh, okay.
So you're correct.
So that it changed. I don't know. That's weird. Okay. Maybe it's setting one of these as the baseline differently. I don't know. I'm not sure. Okay. Well, we could try putting in, we'll see if the predictions come out different. It might just be coded is 6.4509, these two numbers added together. I think they are. 5.7187 plus 0.7327, yeah, would be exactly this number, 6.4509, I'm pretty sure. Yeah, 6.4508. Okay, I know what's going on then, but I don't know why. So for whatever reason, when I click category gender, when I make gender a categorical variable, it is now encoding that into the oh, I see exactly what's happening. Okay, so here gender is 1 or 2, okay? And so this is the intercept, and then if you're a boy, you get coded as a 1, and you will subtract off this value of 0.7327. And if you're a girl, your gender value is 2, and you'll subtract off double this, 0.7327. Okay. Over here, when I said gender is a categorical variable, that will code the boys as a 0 and the girls as a 1. Okay. And so, if you're a boy, you're going to start off at 0.5718 and not subtract off anything. You're going to subtract off 0. And then if you're a girl, you're going to start off at 0.5718 and you subtract off 1 times this value of negative 0.7327. Okay, so leaving the summary as this and leaving gender as 1 and 2, for 1 for boys and 2 for girls, the intercept is artificially a little bit high because everybody gets subtracted off a value. Boys will subtract off 1 times this value, and girls will subtract off 2 times this value. Okay, that makes sense. I get it now. Okay. Maybe I should write that in here. I'll just write that in here. Okay. So we'll see. The intercept here is artificially too big because boys are 1 and girls are 2. So a baby boy will subtract 1 times 0.7327, and a girl will subtract 2 times 0.7327. Okay. Okay, the intercept here is lower. Boys are coded as 0 and will not subtract anything from the intercept. Girls are coded as 1 and will subtract 0.7327 from the intercept. Okay, so there you go. That's fine. Are there any questions on this? And then if you want to make your models more complicated, you can always go to the stats models kind of documentation. I think this is right at the beginning. They start off with the minimal example, and then you can probably just start off looking at linear regression. This is probably going to be where you start, and you can look at examples here for OLS, and they have a bunch of examples. This is just another. It's just a Python notebook, just like everybody else's stuff, right? Or a Jupyter notebook here. Okay. Okay. In Numpy array notation, you would create. This is a little bit closer, similar to sklearn's notation. So when you use sklearn, you create a feature matrix X and basically a score value y, okay, or not score, but you kind of your output values y. So in this case, I'm going to just subset our baby's data frame to our variables age and gender, and then we extract the column of weights to be our y. Kind of the general notation is the feature matrix is a capital X, while the response variable y is lowercase. Okay. Okay, and then if we want to model an intercept, we have to use the function add_constant, okay? Because otherwise it'll just try to fit age and gender directly without an intercept, and if you want to have an intercept, you do stats models add constant x, okay? So you need to add a constant for the intercept term, okay? And because we are using the kind of Numpy notation, we use SM rather than SMF. So not the stats models formula notation, but the stats models notation. Okay, and then for whatever reason, and this I kept getting errors and I was confused, is that when you do stats models OLS is capital. Okay, OLS is capitalized in the Numpy notation. Okay, and then so here I'm calling that model 3. Model 3 fit is we'll call that results 3, and then we ask for the summary, and this part is exactly the same as before. Gender is still left as a numeric variable, and so our intercept for the constant is 6.4509. I guess if I wanted to do model 4, how do I do this? Oh, I forget. Alright, I forgot how I do a categorical variable in the Numpy notation. Alright, I will put that in my to-do. There's got to be some kind of way. Okay. All right. So after you do that, you can create an ANOVA table. Okay, if you're curious about the breakdown of the sum of squares and stuff like that. So here I'm just taking the general results. We could do it for any of the other models. So I could call this table 2 would be sm.stats.ANOVA for a linear model and look at results 2. And we would get the same answers here. Oh, of course they're not exactly the same. Why? Probably something to do with the 0 and the 1 versus the 1 and the 2. Sum of squares, mean sum of squares. Okay. So anyway, yeah. Here we have the ANOVA table, which breaks out your sum of squares and gives you an F-score and a corresponding p-value. And we see that age and gender are indeed significant. Okay. Let's just see what. something wrong. Pandas object has no attribute design info. Oh, jeez. So results 3.summary. Can I not do this? Okay. All right, this is on my to-do also. Fix this. I apologize. Okay. All right, so anyway, you can get the ANOVA table, and I'll have to figure out why for the Numpy notation for results 3, it's giving me an error. I'll have to, I don't know what's going on there. Let me try model 3. No. OLS has no attribute model. Okay. All right, I will fix that. Okay. Once you have your models, you can, however, you can make predictions, okay? And in this case, I'm going to create a dictionary to define our new data. So here I've got a 4-month-old baby, baby boy, okay? So gender is 1, age is 4. And so this is results. So this is using the model where gender is coded numerically. Okay. And so I have this. Okay. And so this will be its predicted weight for our value here, age 4, gender 1. Okay. And if we did it for a girl, we would get 4.98. So if it was a 0-month-old girl, this is what we would have. You can throw in the entire data frame, and you can just do taking that same model and do run a prediction on X, and this is what we would get. And these are kind of all the values. You can you could create kind of some diagnostic plots. Okay, so if you go to stats models examples at the top, so here they fit a regression model. And then, just like as you learned in 101A, you have different tests. So you can check for normality of the residuals, and look at some diagnostic plots right there. Okay. If you've got more complicated ANOVA, you can create interaction plots. So here is, we've got two categorical variables, either weight being low or high, and nutrition being low carb or high carb. And is there an interaction between these two? And these two lines are not parallel, indicating that there is some kind of interaction. Okay, and you can produce that using an interaction plot there. Okay, to do that. Okay, so lots of examples are available here. I don't know. Sorry, I only prepared just a little bit with kind of like the most basic linear regression and ANOVA models. But of course, if you want to fit, you know, a binomial example, you can do any kind of, not binomial, logistic regression. You would use, you know, family is equal to binomial to fit some kind of logistic regression regression thing, right? Okay, and so you would specify family, and in this case, you would do stats models family is probably binomial for the logistic regression, right? So I'm not covering a whole lot of the math because I'm assuming you guys learned it in 101A, right? Logistic regression? Is that just linear regression? There's a little bit of both.
101C.
101C has the logistic,
Yeah.
and you learn that it's like family binomial, right? When you do it in R. Okay, it's the same with Python. You know, in my personal experience, though, if you're gonna go for a little bit more stats-heavy modeling, well, this is probably just my own bias speaking because I'm more familiar with all of R's tools. You know, I think it's fine. Just stick with what you're familiar with. But definitely you can do a lot of stuff. The stats models module for Python is powerful and has a lot of stuff. You can tell that I'm fairly rusty in using it and only know the very basics because I haven't really spent the time going through the documentation. Yeah, when using Python, I probably generally stick to sklearn, and not because sklearn is the greatest, but it's kind of packaged in a way to work quickly and things like that, and it's mostly you're just throwing models at it and you're trying to see what kind of fits and looks appropriate, and you know, maybe we're entering the danger zone a little bit via those tools. You know, if you want a little bit of a more comprehensive regression statistical analysis method, then stats models is probably appropriate, and these things will probably align very closely with, and you can see kind of the influence between that R has had on stats models and sklearn has had on stats models, because the different kind of notations and the ways you fit the models are influenced both by sklearn and R. And I think stats models is trying to kind of pick up and fill in little parts of sklearn, which is, you know, doesn't have as much of a stats enrichment part where you're doing like these regression diagnostics and things like that. So, because like when you take 101A, there should have been a fair amount of emphasis on all of the assumptions going into fitting a linear regression model, right? Like you got to check for heteroscedasticity and you know, are your residuals normally distributed and showing no pattern, and in a lot of big data things, we don't generally check all of these assumptions and stuff, because as we get into these crazier models, the kinds of assumptions that we're making to fit the data get a little bit stranger and probably, frankly, harder to defend and less understood. And so a lot of the, like, is this a good model, is based less on theory but more on results. Like, did we predict well? And if it predicts well, so that's where all of the cross-validation and stuff, all of that part comes in. We just say, like, did we make good predictions? If I throw in new data, does it still make good predictions? And that's how we're evaluating whether our trained model is good or not. So there's less emphasis placed on all of these regression diagnostics in terms of, are we violating the assumptions? Whereas, in your classical statistical approach where you're doing linear regression or you're fitting ANOVA or things like that, there's a lot of assumptions, right? Because linear regression at its heart is based on the central limit theorem that the residuals are centered around the mean that is fit by a line. And so, we're trying to draw insight from these models, trying to understand how the data fit the models. And so making sure that the assumptions we made are valid and good is important, and that's why a lot of emphasis is placed on those diagnostics. And so, the stats discipline is kind of splitting apart a little bit in that you had these traditional methods that focus on the math and the understanding and the assumptions, and are we doing all of these things? And every model we fit, we want to make sense of. We want to say, do I understand this model that I fit? Do I understand what it's implying? Are these implications and are these assumptions, are they valid? And then on the other hand, and that's, and those models are great when you have little data, right? On the other hand, we have the other situation where we've got tons of data. We don't fully understand the models that we're fitting, okay? We got these neural networks. Nobody really knows what any of these coefficients mean. And we just say, okay, I'm in this land of no understanding. Everything's a black box. But if I arrange the black boxes in a good way, it makes good predictions, and I can throw new things at it, and it's still making good predictions. So it's got to be okay, right? And we're kind of dancing on this, dancing a little bit there, okay? And those are probably kind of the different approaches that we're going in. And a lot of research is being done in these machine learning methods to kind of make sure that, it still makes sense. But I think the people who are using these things don't fully understand it. And so we just have a kind of a different way of diagnosing things. We have cross-validation and stuff like that. Training and test sets, yes.
So would that be the difference of using scikit-learn's logistic regression option and then using
stats models?
Stats models. Because I was using it for the project a little bit.
Yeah.
I was I think there was a way to access some of the stats information, but there wasn't as output wouldn't be as.
Yeah, there's still some diagnostic information that you can get, but it's not as emphasized.
It's not like R.
It's not like R. Yeah, definitely. It's different approaches and different philosophies regarding fitting a model to data, right? And I'm not saying one is better than the other. I think there's a time and place for each kind. Just we're fitting things differently. Yeah. Okay. All right. Are there any questions? Sorry, I thought these examples would take a little bit longer, but we just flew through them. So. Okay, if not, we'll end a little bit early. I've got office hours. If you have questions about your project or the other class, you want to look at your tests or something, I'm around. Okay, and with that, we'll look on. We'll see you guys on Friday. I'll try to prepare more examples and stuff for that. Okay, I'll see you then.